Mechanical waves. Table of contents. The first three topics deal in general with waves. The last four are focused on sound waves. Wave motion and types of waves. A wave travels along its medium, such as water or the air, and here we have water. These are water waves. But the individual particles just move up and down or back and forth. All types of traveling waves transport energy. Shown here is a single wave pulse on a string that begins with a vibration created by a person that rapidly moves it up and down, but just once. So it goes up and then it comes down. The wave is transmitted through internal forces in the medium of the string. The wave pulse transports energy between locations, but matter is not transferred. The segments of the string just move up and down. Instead of stopping after one vibration in a medium, a continuous wave is generated if the cause of the vibration continues. For example, the person in the previous slide would keep moving the string up and down to create a continuous wave. There are two types of continuous waves, longitudinal and transverse. Waves that move through matter, like sound, water, strings, springs, and other materials, can exhibit longitudinal and transverse waves, sometimes at the same time. Light waves that will be discussed in electromagnetic radiation are only transverse waves. The motion of particles in a wave, displacement, can either be parallel to the wave direction, and we call those longitudinal waves. That's over here. You've got sound coming out, and you have periods where the molecules get further away from each other and periods where they get closer to each other. Or they can be perpendicular, transverse to the direction of the wave. So this would be an electromagnetic wave. And in this case, the wave, the displacement is up and down, but the direction of the wave is this way, so it's perpendicular or transverse. Particles in a longitudinal wave move parallel to the direction of wave propagation. So the wave is moving this way, but the particles are just going forward and back. The hand is moving forward and backwards, creating areas of compression and rarefaction, also known as expansion in the spring. Each ring of the spring slides forward and backwards in the same dimension as the direction of wave propagation. Particles in a transverse wave move perpendicular to the direction of wave propagation. As shown above, the wave is traveling to the right. However, each section of the spring is only moving up and down as shown by the red arrows. So this piece here, that's kind of at the peak of its up. Next it'll come down, then it'll go back up, etc. But the wave moves to the right. All waves have certain attributes. Shown below, the wavelength, crests, and troughs are marked on the wave. Crests, troughs, and then the wavelengths. Wavelength, or lambda, is the distance between two wave crests or two compressions in a longitudinal wave, right over here. It is also the distance between any two repeating points on the wave that are moving in the same direction. So, right over here is a wavelength, and over here is a wavelength, and they are both equal. A specific medium, such as a spring, can undergo both longitudinal and transverse waves, sometimes at the same time. So this is longitudinal, where you're compressing and expanding the spring in the same direction as the wave motion, and you're moving your hand back and forth. Or you can move your hand up and down, and you get a transverse wave. Or you can do both at the same time. Water waves can have longitudinal and transverse components. The water molecules move up and down, which is transverse, and side to side, which is longitudinal. The picture below shows how the combination of those two components lead to a circular motion. So just look right there, that little yellow dot. It goes up and down, and you can look at any of these others, and you can see they're not moving any closer to the shore, hopefully. So they move up and down, which would be what? That would be transverse. But they're also being pushed to the right, so that's longitudinal. You combine those two and you get a circular motion. Light waves are transverse waves, and they'll be covered in the electromagnetic waves unit. When light, electromagnetic radiation, travels through a vacuum, it has a velocity of approximately 3 times 10 to the 8th meters per second. That's about 671 million miles per hour, or 186,000 miles per second. Sound waves cannot travel through a vacuum, since they are mechanical waves. Mechanical waves require a medium to travel through, like air particles, springs, water, steel rails, etc. Sound travels through different materials at different speeds. While it travels through air at 343 meters per second, it travels through water at 1,500 meters per second and through steel rails at 5,100 meters per second. Wave velocity is the velocity at which mechanical wave crests, or any other part of the wave, moves. A wave crest travels a distance of one wavelength, lambda, in one period, capital T. So we use one of our original physics equations here. Velocity is delta x over delta t. The displacement or distance is lambda. The time is period. We take one other equation. Frequency is 1 over the period. Substitute that in, and we get mechanical wave velocity is lambda times f. The velocity of a mechanical wave depends on the medium through which it is traveling. The velocity of a wave or wave pulse on a stretched string is related to the tension force in the string. And the letter for that is F for force sub T, tension, and the mass per length of the string. So the velocity of the wave in the string is the square root of the tension force divided by the mass per unit length. Light rays, or transverse waves, always move at the speed of light c in a vacuum. The energy transported by a wave is proportional to the square of the wave's amplitude. The intensity, I, of a wave is defined as the power transported across a unit area. So that's power over area, which would be power over 4 pi r squared. That's your surface area of a sphere. Wave intensity is also defined as the average power per unit area during one period of the wave's motion. Let's work some examples. What is the velocity of a wave with a period of 3.0 seconds and a wavelength of 2.1 meters? We start with our givens, period and wavelength. We use the wave velocity formula. Velocity is wavelength over period. Substitute in the givens, and let's check the units here. Meters per second, yep, that's velocity. 0.70 meters per second. What is the velocity of a wave with a frequency of 5 Hertz and a wavelength of 0.20 meters? This time we're given frequency and wavelength. So we use the wave velocity formula, which is wavelength times frequency, substitute in our givens, and once again we get meters per second, or 1.0 meters per second, right? Because 1 Hertz is equal to 1 over seconds. Or another way of showing that is second inverse. What is the frequency of a wave with a wave velocity of 1.6 meters per second and a wavelength of 0.50 meters? We have velocity and wavelength. We start with the wave velocity formula, but we're trying to solve for f. So we divide both sides by lambda. We get frequency is v over lambda. So we have meters per second divided by meters, and that will give us units of 1 over seconds, or hertz. So our answer is 3.2 hertz. What is the wavelength of a wave with a wave velocity of 2.0 meters per second and a period of 5.0 seconds? Givens, velocity, and period. Here's our wave velocity formula when you have period in there. And we want to solve for lambda, so both sides get multiplied with what? With t. So we get lambda is v times t. Substitute in our givens, and let's look at the units. Seconds cancel out, so we're left with meters. Lambda is 10 meters. A string with a mass per length of 80.0 grams per meter, and you have to convert that to kilograms, but in this case we did it for you, is under a tension of 20.0 newtons. What is the velocity of a wave on the string? Just a reminder, always convert grams to kilograms, which in this case was done for us. So here's our givens. Use the velocity tension equation. Velocity is the square root of tension over mass per length. Substitute in our givens. And be sure to take the square root once you divide 20 by 0.08, and you get a velocity of 15.8 meters per second. The wave velocity in a piano string of mass 6.0 grams and length of 1.2 meters is 140 meters per second. What is the tension in the string? This time we have a mass of 6 grams, which we'll have to convert to kilograms. And what do? We move the decimal place over 3 points, so that would be 0.0060 kilograms. Need to do a little more algebra on this one. We have the velocity is the square root of tension over mass per length. We have to get rid of that square root, right? Because we're trying to solve for tension. So you square both sides. So you get v squared is equal to tension over mass per length. Multiply both sides by mass per length. And that's what we have here. Substitute in your givens. So here's your velocity. Here's your mass, again, in kilograms divided by length. And you get a tension force of 98 newtons.